Welcome to Organic Chemistry. Imagine you and your friends are trying to form a circle by holding hands. If there are only three of you, you have to pull your arms sharply inward, creating a lot of tension in your shoulders. But with six people, everyone can stand comfortably. Carbon atoms in a molecule behave exactly the same way when they form rings. Today, we will explore Bayer's strain theory to understand this chemical tension. Now that we have our holding hands analogy, let us look at the chemistry. In organic chemistry, carbon atoms connected by single bonds naturally prefer to arrange their bonds in a three-dimensional shape called a tetrahedron. In this perfect, relaxed pyramid shape, the angle between any two bonds is exactly 109.5 degrees. However, when carbon atoms are forced to join together into a tight, small ring, their bonds are bent away from this comfortable angle. The electrons in the bonds repel each other strongly. This bending creates a built-up tension that we call angle strain. The greater this strain, the more unstable and reactive the molecule becomes. Understanding this chemical stress leads us to the model proposed by Baeyer. To calculate angle strain, Baeyer initially assumed that all carbon rings were perfectly flat, regular polygons. He proposed that we could measure a molecule's instability by calculating how far its bond angles are forced away from the ideal 109.5 degrees. While this model brilliantly explains the high reactivity of small rings, it has a major limitation. It actually fails for rings larger than 3 and 4 carbons. Why? Because in reality, larger molecules are not flat. They twist and pucker into three-dimensional shapes to relieve this built-up strain. Before we can find the strain, we first need to know the actual angle forced upon the carbon atoms. Since Baeyer assumed the rings are flat polygons, we can use a simple geometry formula. The formula states that alpha equals n minus 2 times 180 degrees all divided by n. Here, alpha represents the internal angle of the flat ring measured in degrees. The variable n is the number of carbon atoms forming the ring. The 180 degrees comes from the total degrees in a standard triangle. As the number of carbon atoms increases, the internal angle alpha also increases, allowing us to predict the shape of any perfectly flat polygon. Now that we have the actual internal angle, we can calculate the chemical stress. We compare the actual angle, alpha, to the ideal tetrahedral angle of 109.5 degrees. The formula is D equals 1/2 times the quantity 109.5 degrees minus alpha. Here, D represents the angle strain, which is the deviation experienced by each individual bond. We subtract alpha from the ideal angle to find the total distortion. Because this total distortion is shared equally between the two bonds forming the angle, we must divide the difference by 2. If the calculated strain D is a large number, the molecule is highly stressed. If it is close to 0, the molecule is stable. Let us see this with a concrete example by calculating the strain in cyclopropane. We are given that cyclopropane is a ring made of exactly 3 carbon atoms, and we need to find the angle strain on each bond. To start, we use our polygon formula to find the internal angle. We substitute n equals 3 into the equation because there are 3 carbons forming the ring. This gives us alpha equals 3 minus 2 times 180 degrees divided by 3. This is the first step to finding out how compressed the molecule is, transitioning from a general rule to a specific case. Continuing with our calculation, we simplify the numerator. 3 minus 2 is 1. So we have 1 times 180 degrees, which is simply 180 degrees. This makes perfect sense because a three-sided polygon is a triangle, and the internal angles of a flat triangle always add up to 180 degrees. We then divide this total equally among the 3 corners. 180 divided by 3 gives us an internal angle of 60 degrees. This is the actual angle forced upon the carbon atoms, which is much smaller than the ideal tetrahedral angle. Now we must plug this actual angle of 60 degrees into our strain formula to find the exact deviation. We subtract 60 degrees from the ideal angle of 109.5 degrees. This subtraction tells us the total distortion is 49.5 degrees. But remember, this stress is shared between two bonds. So we divide 49.5 by 2. This gives us our final angle strain of 24.75 degrees per bond. Physically, this is a massive deviation. The bonds are severely bent, making cyclopropane highly unstable and eager to pop open to relieve its internal pressure. This diagram perfectly visualizes the mathematical calculations we just performed for cyclopropane. Look at the top carbon atom. The dashed lines represent where the carbon bonds actually want to be, sitting at a comfortable 109.5 degrees. However, the solid lines show where the bonds are forced to be in order to close the three-sided ring at 60 degrees. The red arrows highlight the gap between the dashed line and the solid line. This gap is the angle strain we just calculated. It physically shows the severe bending stress the molecule endures, explaining why it is so reactive. Now that we have seen a highly strained ring, let us calculate the angle strain for cyclopentane to see how ring size affects chemical stability. Cyclopentane is a ring containing exactly 5 carbon atoms. We want to see if it is more or less stable than cyclopropane. We will use the exact same formulas as before. First, we substitute n equals 5 into the polygon formula to find the internal angle of a flat 5-sided ring. This substitution is the starting point for our geometric calculation, setting up the arithmetic we need to solve. Continuing with cyclopentane, we subtract 2 from 5, which gives us 3. We then multiply 3 by 180 degrees. This tells us that the total sum of the internal angles for a pentagon is always 540 degrees. This represents the combined degrees of all 5 corners of the molecule. We then distribute this total equally among the 5 carbon atoms by dividing by 5. This gives an internal angle of 108 degrees for each corner. Notice how much closer this number is to the ideal tetrahedral angle. For our final step, we calculate the exact strain using our deviation formula. We subtract the actual angle of 108 degrees from the ideal angle of 109.5 degrees. The total distortion for the entire angle is only 1.5 degrees. Because this total bending is shared between the two bonds that meet at the carbon atom, we divide this small number in half. This gives us a final angle strain of just 0.75 degrees per bond. This is a very tiny deviation, meaning the bonds are almost perfectly in their natural position. Cyclopentane is therefore a very stable molecule. So, we have proven mathematically how ring size affects strain. Understanding Baeyer strain theory is crucial because it explains why certain chemicals exist in nature while others do not. For example, cyclopropane is so strained and reactive that it was once used as a fast-acting surgical anesthetic, but it had to be abandoned because it is highly explosive. On the other hand, rings with 5 or 6 carbon atoms have very little strain, making them incredibly stable. This is exactly why the most important molecules in your body, such as the glucose that gives you energy and the DNA bases that store your genetics, are built using 5-membered and 6-membered carbon rings. Nature always prefers stability. Let us review the key takeaways from today's lesson. First, Baeyer strain theory measures the instability of carbon rings by calculating how much their bond angles deviate from the ideal tetrahedral angle of 109.5 degrees. Second, small rings like cyclopropane suffer from severe angle strain, making them highly reactive and unstable. Third, we learnt that the closer a ring's internal angle is to the ideal value, the more stable the molecule will be. Finally, remember that Bayer's model assumes flat rings, so it fails for rings larger than 4 carbons, which actually pucker to relieve strain. You now understand the fundamental geometry behind organic ring stability.